Compound eyes are common in natural systems. Here we're looking at compound eyes associated with insects, where they're consisting of ommatidia. Each ommatidia is a single lens and then a photoreceptor cell and a neuron. These are good for navigational guidance, but are not very useful for forming wide field high resolution images. Images of the ommatidia are beautiful. This is the Arctic krill in an electron microscope, picture taken by Gerd Alberti and Uwe Kills. But as we get into more advanced organisms, we want more advanced processing. So humans also have a compound eye, but in our case, we don't look at the individual response of the photoreceptors. We have to process the image as a whole, for which we have the entire visual cortex. Cameras have been much more literal than this. The traditional cameras process frames, process individual pixel values, and don't have this advanced neural processing. But for reasons we'll talk about in many of the coming episodes, it's essential for the future of cameras to evolve to systems like this that have compound eyes for artificial cameras. Here's a camera from Transformative Optics, which I'm affiliated with for full disclosure. This camera has 20 micro cameras. A very different reason that you would use this kind of camera than the reasons you use ommatidia-based systems. The ommatidia systems could be useful for robotic guidance or smart hands, but if you want to form high-resolution images, it's necessary to use camera arrays because it's simply impossible to get all the data in the optical field from a single camera. But when you go to array systems, you need the ability to stitch the images together. So you need to build a neural processor or artificial visual cortex that can manage and present the data. Let's look at how data is presented as an example from this camera. You can see the wide field image that was recorded at this site in Spain. You see the clouds moving, media streaming. We could stop time and make the clouds go backwards by clicking on the forward scan, or just let time run. And under here you see the trees blowing in the breeze. Zoom back out, pan around the image. Over on the hilltop here, looks like there's a person that's just summited the hill and his friend coming down through the bushes next to him. It turns out that there's a drone in the sky in this video, so if we go and click over here, we can find the drone, and we see a bird flying behind the drone. So again, this drone is a kilometer or so away, so the resolution we have on it is not enormous. I mean, we stop time and just on the drone and the bird. Computational imaging. Episode 62, Image Fusion. Episode 61 talked about extrinsic calibration, and we found the key points in images and then used key point matching in homography to relate images taken from two different cameras to each other. Today we extend this to talk about panoramic image fusion, and we use the code that's on the Jupyter notebook that's on the GitHub site as shown on this slide. The key to our combination of images last time was the homography relationship between planes matched through a center of projection. So here's the center of projection. For example, a camera might be imaging this plane x prime, y prime onto this plane xy through the center of projection. The points xy need to lie in this plane, which would give us a linear equation relating those points. X prime, y prime need to lie in this plane, which gives us a linear equation relating those points. And then the points have to lie on the line through the center of projection, which is another linear transformation. So we can combine those set of linear relationships to get this homography relationship between points xy in this plane and points x prime, y prime in this plane. So then given a point in the x prime, y prime plane, we can find the corresponding point back in the xy plane through this transformation after we've done the homography matrix multiplication. Now we need to find the homography if we just have planes of arbitrary position from two different cameras. For that, we used key point matching. Here is an example of a couple of pictures of the Wyatt College of Optical Sciences at the University of Arizona, looking to the right over here to the stadium, and to the left, looking at the old Minell building, the new Minell building, and the Grand Challenges Research Building. Now you see the horizontal lines going here. Those are key point matches between these images. To find those key points, we use the scale invariant feature transform, the SIFT algorithm, and then we matched the key points and then drew those lines. And then once we have the matches between the key points, those points have to obey the homography transformation, and given a known set of points, we can use this ransack algorithm to find the homography that most matches the set of points that we have. Once we have the homography, we can transform the images. So here's the RGB versions of those two images, and then we've used this OpenCV warp transformation with the homography matrix to transform image 1 to the viewpoint of image 2. And now you see that the space is expanded because of the points correspondence between these 2 points. So we're in the image 2 space, and image 1 doesn't match in image 2 space until we get over here to the 3000th pixel or so. And now the full image is some 7,000 pixels across or larger if we use the full version of image 1. Now we can just combine these images together. We're just choosing to use image 1 where image 1 is non-zero, and then image 2 where image 1 is equal to 0, and we get the stitched panorama going from images that were 4,000 images or 4,000 pixels across now to a 8,000 pixel stitched panorama. Of course, here all we've done is align the images to each other using the homography transformation and then choose one image or the other, and so we see stitching artifacts. These algorithms to combine panoramas can get obviously much more sophisticated. There's commercial software, a variety of types available to do this better. There's also open source software in the Huygen platform that combines key point detection, matching, and then blending. And so here we see a picture of a set of 61 images of Venice shot by Jeffrey Martin, which is on the Huygen website. And these are registered and combined, but not blended. And then if you do some vignetting correction and blending, you can get a well-formed panoramic stitched image. We won't deal here with the details of blending algorithms. We're more focused on camera design and what kinds of data we should sense, but those algorithms are out there. But these algorithms are uniformly being replaced by neural processing algorithms. Our focus in these lectures is on how we should design cameras to capture the light field, how we should design cameras to get as much information as possible. And what we see, generally speaking, is that no camera could capture no single aperture camera can capture all of the data that's in the data cube, and so we end up wanting to build camera arrays. Here's a paper from a couple years ago in Light Science and Applications by Xiaoyuan Yuan and Lu Fang's group with contributions from myself and Qinghong Dai. And the idea of the paper, the motivation, is definitely to think about how you could use distributed sensor resources and then neural style processing to create understanding of the world, not just an image, but a real model of the world, or as much data as we can get from a camera array. And so now we have a fundamental change in the nature of what a camera is. We've gone from something that just forms an image to something that captures data, that we're going to use that data to recreate the world. So something much more along the lines of human processing is suggested by these crania shown on this slide. But we're a long way from actually getting these full systems built. In this particular case of the hierarchical camera, we have a variety of wide field and narrow field cameras that we're going to combine in a variety of ways. If we thought about sampling every pixel, every point in the data cube, that would be the structured camera that we would get all of the data possible from very uniform sampling. If we do that, we're unlikely to get a good sampling of the world because the world has regions of high interest and regions of less interest. Here, for example, you might want to get faces and license plates with some accuracy, but the broader context of the trees and the scene you may not need the same resolution on. This, of course, is similar to foveation in human vision, and that is a way to reduce processing cost and get more information. But how to implement it, what it really means for cameras, is definitely a topic of continuing interest. Now, once you have this hierarchical data, the question is how to combine it. So here's, I'm going to go through some examples of a way to take data from hierarchical arrays. In this case, we're thinking that we want to image the scene shown here. We could have high-resolution monochrome images with low-resolution color images or different scale images. So we don't just have to think about we're going to have images looking in different points that we're going to stitch. We can have cameras that sense data of a variety of types that can be interesting in various scales, and then we want to combine that data. The key to this is that we no longer, when we have this heterogeneous data, we can't simply just register the cameras and blend the images. We need to do some kind of feature-based imaging. So we could take, for example, the images from the cameras we want to blend and then extract feature maps from those images and then apply some kind of transformation to turn those feature maps into a resulting image. Here we were referencing a couple of papers from my group where we used physics-aware transformers. So the physics-aware part means that the cameras are aware of which features are coarsely aligned in the same space. We have to do camera registration in order to coarsely align the feature maps, and then from the feature maps we use a transformer architecture to recreate a combined feature map that we can use to generate the image. The details of this network are described in this paper, which is in the Journal of Imaging Science and Technology and also available on arXiv. The left part A is the feature extraction strategy to find features embedded in each one of the images, and then we use an attention engine, which is something that transformers use to relate features to each other and combine them. And then the D here, the C and D are details of internal structure of the transformer architecture that's used to recreate the combined features we use to recreate the image. So this kind of more advanced non-feature-based image fusion instead of pixel-based image fusion allows you to do things like this. You have a low-resolution bare image, a high-resolution monochrome image, and you can produce a combined color image in high resolution. And so here's comparing on the left features of the low-resolution bare image, the RGB image, and then on the right the combined high-resolution color image. Reasons you might want to do this is that you get better light sensitivity in the monochrome image, and you could vary frame rate. You can vary color sampling in a wide variety of ways. You could do things like, rather than using bare sampling, you could build camera arrays that have RGB cameras. So here we have a red, green, and blue filter on the cameras, and then you can combine them with this these architectures to create a all-in-focus color image. This allows you to have independent exposure for each of the color channels, independent lenses, independent focus for each of the color channels, and so gives you a much more dynamic and open sampling system that will get better information, as suggested in the heterogeneous array camera, than a single camera ever could. Here's another example of a high-resolution system. In this case, we have a wide-field camera for the low resolution and a narrow-field camera at a longer focal length for the high-resolution image. And then again, you can combine kind of arbitrary type data with these kind of architectures. And so on the left here is the low-resolution shot of the fire alarm. In the middle is the high-resolution monochrome, and the right is the high-resolution combined image. So this field, this idea of how do we build architectures for processing data from heterogeneous camera arrays is very much in its infancy. So what I've shown you here is a couple of algorithms that allow us to do that with transformers. There's also groups working on using neural radiance fields for this. Many episodes ago, we talked about neural representations, where we build a neural network to regressively model the data that we've captured. A neural radiance field is a system that does that for a variety of camera views. Could do that, as shown here, for a camera array. So you can take array camera data and represent it in a combined neural structure to regenerate the data. It's been typically used for three-dimensional imaging, but in principle could be used for any kind of array camera architecture as well. Basically, it's regression on the things that you know to regenerate things that you don't know. Alternative strategies have been things like Gaussian spotting, where you take camera data projected into the space of the real world and then reproject different camera views. So you can also do this for arrays of cameras. But again, this field is only starting, and we don't really have now architectures that that are fully capable. And so what I've shown you in today's episode is, first of all, the rudimentary traditional strategy of you have some images, align them and blend them. Obviously, that strategy needs to evolve to account for data that we capture from more heterogeneous, more interesting camera arrays. Over the history of cameras, we started with film, where we just capture an image, and then electronics. Also, initially just sampled the image and raster scanned the raw image out. Over the last 30 years, electronics had to move away from capturing raw video to capturing compressed data, which allows you to capture more and transmit and store more. And so to do that, ASICs were developed, chips that would do automatic encoding of JPEG data or H.265 data or any kind of compression standard. Just emerging now are neural processing architectures that will do that kind of processing. We're evolving more and more towards something that will be like this idea of a visual cortex, that we don't just sample pixel data and read it out, that we sample data and process it in real time. But it's very much a work in progress. Our focus in these episodes is how we should build the front end. Like what I've shown you today is we can capture different fields of view, different resolution, we can capture different color in different cameras, we can capture at different frame rates. How do we decide how to build the ideal architecture? And that's what we're going to start to talk about in our next series of lectures, where we begin to talk about the relationship between the object data cube, all the descriptors we have of the object, how the object gets transformed into the optical field, and then how we decide which parts of the optical field to measure when we want to build a camera.